Yo, what's up, everyone? Um, we're in the new quarter, and honestly, I'm thrilled. I think I hit it this time pretty well, but like, I really, really hate the end of the quarters. I hate the grading. I hate dealing with all the students who just copy and then, ask me to grade their stuff within one day, even though it took them like 2 months to do it. So I always pretend to be nice, and I say this here because, only my bollies are listening. So we're in the new quarter, and first things first, like I'm always going to start the new quarter with a week one. So it's not week nine of the course anymore. It's going to be week one again. And that kind of always helps us time the quarter. So you know if you're in a week four, you're about halfway through. You're in a week six, you kind of are close to the end. But we're starting back at week one for the second quarter. And the other thing that's kind of cool is that this is the last lesson for this quarter. Um, no, 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 no. This is the last lesson of this unit. And after this lesson, we're going to have a test. So I'm going to change things up a bit to make sure that there's enough time, people don't get too stressed. So we're going to have this problem set. Then I'm going to assign you the project with the project video as the second problem set this week. And then next week will be just straight review for the test. Okay? So this is our last lesson for this unit, and it is a hard lesson. And I really like it too. And obviously I spent a lot of time kind of trying to come up with it. And if we get through, I think it'll be really satisfying. This is a lesson I didn't teach last year, so it's something that I've missed in the past, but it's something that kind of ties the unit together. So let's read the question and we'll go from there. And it says the following two scatter plots show the average speed and distance for Amazon cross-country delivery trucks compared to how many gallons of gas they use. So if we're looking at both of them, it's another typical situation where we have two scatter plots testing the same thing, and they're trying to figure out or compare how far a truck drives across the country to how much gas it uses, and then how fast it goes on average compared to the gas it uses. Okay, because we know, the longer the trip, the more gas you're going to use. But something else we know is that the faster you go, usually the slower or the more gas you use, right? So if you go fast, the more gas you use. But what's even more important here is to kind of address what I would consider an elephant in the room if you're thinking really heavily about this stuff. And that's the idea that, not every scatter plot is going to look linear. So when we look at both of these scatter plots, this looks like pretty much every scatter plot we've done so far, and I hopefully you're comfortable with it. This is like moderate strong to strong correlation, something like 0.75 to 0.85. And all the points make a sort of line, right? The problem is, this is not always going to happen, right? And, a lot of you took Algebra 2 with me, and the whole point of Algebra 2 is to talk about all the different kinds of functions you can have, right? We can have linear functions, which you always start with, but we know that there are 8 types of functions, in fact, and another one is quadratic, right? So if we look at this second graph, I spent a lot of time trying to find or think of an example that was really logical. We know that if you drive really slow, your car is going to take a lot of gas because it's just going to take you longer to get there. And we know that there's a sweet spot around 60 miles per hour where your car is going to be the most efficient. But if you go any faster, especially if you're a truck, you're going to burn gas really, really quickly. Okay? So in real life, this is kind of the shape that the speed you go and the gas you would use would represent. And it's not linear. Okay? You can't really draw a line of best fit on here if you're going to draw a straight line with a slope and a y-intercept, right? So if I look at the second graph, they tried a line of best fit. The line is mostly going down on the right side, and then there's just a few points pushing it up. But this line really doesn't represent what's going on here. You always can try your best, but in this case, if someone were to ask you, do you think linear regression or a line of best fit is appropriate? You would have to say no here, okay? A line of best fit makes a lot of sense here because our points kind of represent a line. But in this case, linear regression doesn't seem appropriate. And if we think something quadratic would be better. And I made the points kind of perfect so you could see it, but you could see kind of a up and down thing going too. But think that something like that from last unit I mean, yeah, last year or whenever you took algebra, would represent my data much better. Every point is really close to this line. Okay, so let's answer A. And it says, does linear regression seem appropriate for the graph on the right? We would say no, and a quadratic model would be better. Before we proceed, what I want you to know, the good news, is that you're never going to have to draw a line, but you'd call it like a quadratic graph of best fit. You're never going to have to do that in this unit. Okay, if it doesn't look linear, all you have to do is say it's not linear. Okay, you're never going to have to find an equation. So in that case, I think it's pretty easy, but that is like now the final thing that you're going to look for when you're looking at a scatter plot. Is, does it actually look linear? Is there no correlation, or could it actually be represented by another function? Okay, so that's A, and then B looks really confusing, but I want to explain it because if we do it now, the project is going to be even easier too. And it's really important here because, well, first let me just read it. It says the following shows each data point on the scatter plot above, as well as their expected value and their residual. Fill out any missing information. So the way I made this scatter plot, right, was I had a bunch of data points and I plotted them. So you can think of these, and then they are on the next page. So if you're printing this, definitely print it not that side to side because it's really important. But these are all of my data points. And another thing that we can always calculate is the expected value at each of my data points and the residual. So I've asked you to calculate an individual residual before, but we also have to be able to be comfortable if we're given kind of random information, right? So we know that the formula for the residual, which means how far away the point is from the line, is the data point, the observed value, minus the expected value. So if I'm looking at this first one, this first row, I'm just trying to get us familiar with seeing tables like this. All this is saying is my first data point. Oh, I flipped them, that's fine. Right? Yeah, I did, yeah, that's fine. 45, comma 590. So that's that data point. And it is 492 is its expected value. That's what the line of best fit says. And that's 97 away from the point. Okay, so this tells you the data point, what the line of best fit says is expected, and then also the residual. So if we see things missing here, we're just going to stay consistent with our formula, and it should be really easy. If I'm trying to find a residual, and I have my observed and my expected, all I have to do is observed minus expected. Because the definition of a residual is how far away is the point from the line. So that's how we do that, and we can do the same thing here. Remember that if it's negative, so the second one's going to be negative, that means my point was below the graph. By similar logic, we can actually fill out the rest of these too, right? So if we have the observed value and the residual, we can set up a small equation for ourselves. And same thing here. So here, we're missing expected. So 390 minus x equals negative 69.62. Here, we're missing observed. So x minus 450.55 equals negative 75.55. So I'm going to do those to fill those out, and then by similar, well actually I'll just do those two. Okay. And then I want you to skip the second one for the sake of time, so don't worry about that. But the last one that this table asks you to solve is both the expected and the residual. And we know that the way we do that is we plug the x value from the equation into it to find the expected value, and then we calculate the residual. So I said that quickly, but hopefully it makes sense. Okay, so if you're getting all the way through that, then you're in a really, really good spot. And the next part of this is the big tricky part, in my opinion, and also the major part of the lesson, and that is the last big concept, which is the residual plot. And here's the big idea. Every unit in the beginning of the year, there's like multiple types of graph that you have to be familiar with, and there's a second graph in this unit called the residual plot. Okay, and what is important about this, and what's interesting, and all a residual plot is graphing the residuals and not the observed values for each of your x values. So let me say that again. But we have our scatter plot here that measures the speed and the gas used by each car. But every single data point, what we just kind of discovered was that every data point has a residual, right? So this point is above the graph by that much. This point is above the graph by this much. These points are all below the graph. And instead of graphing their actual distance, their gas used, we can instead graph their residual. Okay, right? The first residual was 97 on the data point 45. The second residual was like 550 at 47. So when you have a residual plot, and I highly doubt you'll have to make any more of them. I won't make you draw any more other than this one. You mostly have to analyze them. Okay, so hopefully I haven't lost you. This is the big part of the lesson, and we're actually closer than you think to done. But if I'm making a residual plot, the x stays the same. The speed stays the same, because we still want to plot every single data point. But instead of plotting their gas used, we're going to plot their residual. So what's really important here is that if you have a residual plot, to put a line with 0 in the middle, because some of your residuals are positive and some of your residuals are negative. So let's look like always on a graph and figure out 100 is my biggest data point, and well, I actually see 158. I see 158 as the highest, and then negative 80 as the lowest. So I'm gonna go by like 20s here. Okay, now all I have to do is just plot each of my residuals. So my first data point was 45, 97.71. My second data point was 52 points away from the graph, so 52, 47. And then we keep going. So I'm going to do it while going speed mode. Before I go speed mode, I did this point wrong. The next one is 47, so like here, it was 47, 52 on this one. And then 49, and then we'll go. Okay, so that's my first residual plot. And now that we have this plot, I'm only going to do the one because I'm going to make the next part of the lesson, like the last part, a really big part too. Okay, actually what I've decided, and this will be a new thing for me, but I think that I know how to do it pretty easily, but I'm going to put the residual plot for the second graph here, like edit it on, and then talk about them both because I know exactly what it's going to look like. So I think I can do that. This first one is the quadratic, so this is miles per hour. And then the second one is miles driven. Just because I don't want to draw the second one, I can do it on my computer really easily. But if there's been a bit of disorganization as we construct the plot, that's kind of by design, just because I always want you to know where the graphs come from. Now we want to figure out what we can do with a residual plot. And what's really interesting is before we look at this residual plot for this graph, let's just think about what's happening here. If you try to make a line of best fit, so let me make that a little easier to see. This is our line of best fit, and we know that this line doesn't really work. And one way that can be really obvious from this residual plot is that there is a shape of the residual plot that's really similar to the shape of the scatter plot. And if we look, we notice that all of the points on the ends have residuals greater than 0. And then all the points on the inside have residuals that are less than 0. Okay? So that is always going to indicate to you, if you see some sort of shape in this residual plot, that shape is usually going to match very similarly to the initial graph, and that's going to tell you that linear models don't work. Let's now look at this second scatter plot. So if we look at this residual plot, the values are above the line, kind of dispersed really randomly. And if we are going to compare that to this, and I think this is really fascinating. This represents a linear equation because some points are above the line, some points are below, right? There's no pattern to my data other than it generally goes up, right? So some data points are above, some are below. In this model that's not linear, all of the left and all of the right are above, everything in the middle is below. Here, it's kind of random. And the residual plot really just measures how far away every point is from the line of best fit. So it actually centers the line, and I think this is really powerful. If we look, the residual plot that's on the below looks just like this if our graph was like here. I hope that kind of makes sense. I don't even know. But the points are above and below, right? Some points above, some points are below. So if you are ever given residual plots, if there's a pattern, that means it's nonlinear. If there's no pattern, it's linear or random. And that's what this is saying. Okay, so first is a typo. Let's read the question. It says the following 4 residual plots show average temperature in October in 4 cities: Pinole, Potomac, St. Louis, and Singapore. And the key to this first, to know if you're looking at a residual plot or a scatter plot, because they do look really similar, is just look at the Y, right? If it's a residual plot, it's measuring all of the residuals, okay? And secondly, a residual plot's never going to have a line of best fit. So all of these have a line that I want you to notice, but that line is 0, right? We know that all of the points above that line have positive residuals, and all the points below that line have negative residuals. So those are kind of our keys to know it's a residual plot. And all this is asking is if we're looking at the residual plots, which ones look like they're linear and which ones look like they're nonlinear. And all you have to look for is a pattern. 2 of them look random, right? And random is not the worst thing for a residual plot. It's not like a scatter plot where random means no correlation. If you see a random residual plot, that means it's either linear or no correlation. What we're really looking for in a residual plot is anything that looks, staged or like not a line. So this is definitely going to be non-linear. And so is this. And hopefully everyone, like, even if this has been kind of a tricky lesson, that at least makes sense. So the residual plot measures how far every point is from the line. And if there's a pattern here, that means there's probably a pattern on the scatter plot itself. So if it's just based solely on the residual plot, what appears to have nonlinear regression? And we just talked about that. Okay, so now we actually look at the scatter plots themselves. And I forgot to say this before, but I love this question. It took me forever to write because these are like the 4 places I've lived in my life. I've lived in each of these places for at least 6 months, and all of their weather is true. But we're really trying to figure out which of these scatter plots results in the residuals over there. But first, in Pinole recently, like, we've had our hot days and our cold days. So something like this, which I feel bad for my Algebra 2 students, but this is kind of what a trigonomic function graph looks like. So this one is definitely not linear as a scatter plot. And this one's definitely not linear. This is my hometown, Potomac. And this is when it starts getting real cold. So if I'm trying to match, we know we do a lot of matching. The ones that were nonlinear are usually going to look exactly like their residual plots. And let me explain why, specifically with number 2, and I think this is so fascinating. And if you get this, you're in a great spot. But if they attempt this line of best fit, it's going to be really close to horizontal. And if you see a really horizontal line, that usually indicates that there's not that much correlation, right? Because as the days go on, the temperature's only increasing by like 2 degrees. So all of these graphs that kind of have different shapes are going to be really close to this linear line, this straight line of best fit. And if this is the line of best fit, the residual is going to match it, right? Because the line of best fit is super similar to the line 0. Right, these points are above the line, these points are below the line, these points are above the line, just like what's happening on the residual plot. So this is going to be B, and then 1 and C line up, and I just want you to make sure you understand the logic, where this is more like an exponential graph, where all the points on the sides are above and all the points on the inside are below. So this is not linear. Like, this line kind of represents what's going on, but it's definitely better represented by something that is curved, okay? And then the final thing we have to talk about is 3 and 4, St. Louis and Singapore. And one of them has really strong correlation, just steady temperatures getting lower and lower, and one of them is random. And then what sucks is that A and D both look really similar, right? They're both random. And the gist here is that both linear regression scatterplots and random scatterplots are going to look the exact same as residuals. Because here, think that the residual plot is just plotting this, and it's really random what points are above and what points are below, okay? So think that linear regression, it can be random where the points are, if they're above or below that line. And then if it's random, it's the same thing. So some points are above, some points are below. Both of them result in similar scatter plots. You're only going to, or residual plots, you're only going to have like a really funky shape if it's nonlinear. Okay, so we can't even distinguish between these two, and that's really important, and I'll make sure to cover this in review as well. Definitely a long video, but I think worth it. So for these final two, those are the last two that I'm missing, A or D. Alrighty, that's that. If that was confusing, don't sweat it too much. But yeah. Woo!